I don't see the number of people.
So it's under the attendees tab.
Oh, there it is. Ah, thank you. Well, it's, you know, nobody shows up on these things on time. We have 40 people registered, so.
Great.
Welcome, everyone. We'll give it 1 more minute before we get the webinar started. And just want to let you know, the webinar will be recorded. So it will be on the AGU YouTube channel, as well as the Global Environmental Change section website.
Oh, good. Okay.
Hello, everyone. Welcome to the Global Environmental Change section of AGU's Early Career and Mid-Career Awards webinar series, and Global Environmental Change section of American Geophysical Union Awards, Early Career Awards, as well as Mid-Career Awards for Global Environmental Change section researchers. And it's my great pleasure to introduce Dr. Julie Bringham Greta, the president of the Global Environmental Change section, to introduce the speaker of today.
Thanks very much, Yuhan. Welcome, everyone. It's great to have you here and as part of this webinar series. The Global Environmental Change Early Career Award is given annually and recognized as early career scientists or a group of early career scientists for outstanding contributions in research, education, social impacts in the area of global change, especially through interdisciplinary approaches. This year we have gave out 3 awards, and each of them comes with a nice award certificate and a monetary prize of $1,000. And we hope to present those things to them either in person or virtually at our awards ceremony at the AGU in New Orleans on Tuesday evening between 6 and 6:30. It's a short but hybrid program, and so you might want to put that on your calendars. So we have 2 speakers today, 2 of our early career winners, and I'm going to introduce the first one. That's Alex Cunning, and then I will introduce the second one after she's finished, and we'll have Q&A at the very end of the program. So Dr. Alex Cunning is an assistant professor in the Department of Earth Science at Stanford University. Her research is focused on the interactions between global carbon, water cycles, especially as related to plant hydraulics and to the effects of small-scale trait variability in regional scale ecosystem behavior. And she's also a recipient of a NASA Early Career Award and an NSF Early Career Award. So we look forward to hearing from Alex. Take it away.
All right, well, thanks, Julie. So I'll be talking today about the use of microwave remote sensing of plant water stress response, which is something that my group has been working on for a couple years now. So before I really get going, I just wanted to kind of highlight the contributions without whom this talk would not have been possible, which are the postdocs and students in my groups, Mustafa Moomin, Natan Holtzman, Yanlan Liu, Krishna Rao, and Jackie Fortin-Fleffel. All right, so why might we even care about plant water stress response and whether or not we can use microwave remote sensing for it? If I manage to advance my slide here, I just want to give a brief overview of that, right? So one key reason is sort of on the hydrology side. The plant water stress response has a significant impact on transpiration and therefore on the partitioning of the surface energy balance into sensible and latent heat. So that effect of the plant water stress response is going to feed back all the way to sort of the evolution of weather and climate through land-atmosphere interactions. And just from sort of first principles, right, the sort of water balance that you see in the bottom of the slide here, also that effect of water stress response on evapotranspiration is going to have just an effect on the rest of the available water fluxes and eventually their availability for water resources. Plant water stress response also has a big effect on the carbon cycle, most directly just through its effect on vegetation growth. You see that in this time series here. These are two different species growing right alongside each other in the same conditions, but with different plant water stress response, and the photosynthesis rates are quite different. And then, as I'll talk about later in this talk, there's also quite significant effects on drought-driven tree mortality and on fire. All right, so I keep using this phrase, plant water stress response, and I'm going to now introduce another phrase that I'll mention a lot here, which is vegetation water content, and that's really how the microwave remote sensing comes in. Now, just to go over that, vegetation water content is really just the water that's actually stored above ground within the plants. It's just going to be the balance of the water coming into the plant through root water uptake and the loss of water through transpiration. Now that's kind of relevant here because it turns out that vegetation water content is deeply intertwined with the water potential that actually drives the flow of water through the plant, and especially the stomatal closure that controls transpiration and photosynthesis. Now, depending on your background, that may or may not sound super familiar, right? Because the classical view in hydrology for a long time has just been to basically ignore this vegetation water content and say, hey, transpiration just depends on soil moisture. That soil moisture instantaneously gets from the roots to the leaves. And that's all there is to it. But there's really increasing evidence in recent years that it's not quite so simple, and that movement of water through the plant and that vegetation water content really has an effect, especially during drought conditions. And you see that here in this slide. This is a paper that we published a couple years ago, where what we did is we just wanted to compare this effect through a modeling exercise. So for 40 different FluxNet sites, we went and we locally optimized a standard empirical model of ET just as a function of soil moisture and other things. And then we compared that to a model of hydraulics that actually accounts for vegetation water content. And you see on the left here that, on average, when we look across the entire record period, that doesn't really make much of a difference, right? That's why this classical view in hydrology has been successful for so long. But when we go look at the high vapor pressure deficit, high atmospheric aridity conditions, where there's a lot of water stress, then you start to deviate from this one-to-one line, and this hydraulic model that accounts for vegetation water content does a lot better. And we're not the only people who have shown this. There's a ton of other papers out there making this point as well. So if we're interested in this, one of the first things you need is good measurements. But it turns out that's particularly challenging in this context. Well, actually, one of the reasons it's challenging, I think, is maybe not particular to plant hydraulics, but it's just that it suffers from the same in situ logistical biases that most measurements do, which is that if you look at most measurements across the globe, most of them are in the mid latitudes where there's just easier access and more funding for research. Another factor here is that, like I mentioned before, you oftentimes have plants growing alongside each other that have a completely different plant water stress response set of traits, and therefore a completely different effect on plant hydraulics. So you have a lot of variability that you need to make sure you're sampling. And what I like to argue is that remote sensing is really the answer to both of these challenges. It can get you global measurements, and it naturally aggregates over that small scale variability. And particularly what I'll talk about today is microwave remote sensing as being the big solution here. And that's mostly just because microwave remote sensing is directly sensitive to water content of plants. Now, I should clarify, it's not just plants, right? Microwave remote sensing is actually sensitive to water content in the entire land surface, including in the soil. So traditionally, these data sets have mostly been used for soil moisture remote sensing and all of its applications. But there's also this dependence on vegetation water content that was usually just kind of treated in the algorithms and ignored. And thankfully, we have multiple electromagnetic polarizations to isolate both of those signals. And so when we do that, what microwave remote sensing allows us to measure is this quantity known as the vegetation optical depth, or the VOD here. And we have pretty good evidence, like I was sort of implying earlier, that that's basically linearly proportional to the vegetation water content, that mass of water per unit area that I was describing in the beginning. And then we can just do a little bit of algebra to better understand what that is and what it can do for us. If we just multiply and divide by the total above ground biomass, that M sub tot here, what we see is that the vegetation water content that we measure with remote sensing is a combination of a sort of relative water content, amount of water per unit biomass, and that biomass itself. Now, knowing and understanding biomass variations has a ton of applications itself. So there's been a lot of interest in using VOD for biomass. But I'm personally very interested in the second signal here and whether or not we can learn something from these relative water content variations. And I think that relative water content variation is really useful for understanding plant water stress response, just because it's, again, really closely tied to the water potential that actually drives the plant water stress response. Plant physiologists have known this for decades. In this paper, we grabbed a couple curves from the literature, but curves like this that relate relative water content and water potential in the xylem or another plant component have been around for decades. They're known as pressure volume curves, right? They even have their own name. So we think that there's at least an opportunity here to use these data sets to understand water potential and what sort of water stress plants are actually experiencing. So we went out and we measured this. We put an in situ radiometer right above an oak canopy in Harvard Forest a couple of years ago in Western Massachusetts. And that's an L-band radiometer, very similar to what you might see on a satellite. And then we measured the leaf and the stem water potential at the same time. And as you can see on the right here, when we look at the diurnal cycle, which is easiest because these measurements are pretty laborious, we see a very close match between the leaf water potential and the VOD, and in a slightly shifted way, some resemblance to the stem water potential cycle as well. So I think this and a couple other papers I won't go through for the sake of time really give us a good feeling that this is not just a hand-wavy argument that I was just making, but that there's actually information about water potential in these data sets. All right, so that's all well and good. What I'm going to do in the rest of this talk is try and give you some examples of that information content actually being useful and how we might go about and use that. And one thing that we've done a lot is used microwave remote sensing to map different plant hydraulic traits. So as a first example here, we used diurnal variations in VOD to map this ecosystem scale isohydricity property. Now that's normally a species-specific trait that we sort of upscaled. And what it really is it's a combination of stomatal traits that control stomatal closure and xylem traits that control how fast water moves through the plant. Essentially what it is a measure of sort of how well leaf water potential stays relatively stable instead of drying out as a soil dries out. Although I think Kim, among others, our next speaker, has shown that it's a little more subtle than that. But anyway, so roughly speaking, we have this isohydricity here. And I would say that this map is sort of pretty typical of what we see when we try to map ecosystem scale plant traits with remote sensing, right? There's a ton of scatter here, but that's not noise. That actually makes sense, right? There's a lot of variability that's being captured. Different species growing in different places, effects of heterogeneity within each pixel, and how that sort of interacts to control the behavior. A ton of intraspecific variability for these variables due to land use history, disturbance history, local climate, soils, et cetera, et cetera. So there is some scatter in this plot. That's not just noise, but that actually has information. And at the same time, I think, you know, we can you can look at this and maybe feel a little bit better because there's patterns here that you would expect. So for example, really anisohydric corn belt, for example, in the US is consistent with our expectations of crops growing fast, being bred to grow fast. And so in fact, you know, that beyond those signals, that scatter that I was just mentioning has information, and we've been able to show for different land cover types how that then explains different carbon flux patterns. So I've done that, as you see in the bottom here, for grasslands, and other groups have done the same thing for forest with these isohydricity data. Now, isohydricity, like I said, it's a species-specific trait that plant physiologists know, but it's got a little bit of a disadvantage because it's very difficult to model sort of put together a land surface model with these data. So we asked ourselves, you know, can we use data assimilation as shown in this slide to map traits that modelers might actually want related to xylem and stomata? And when we do that, we get something like this. So those of you familiar with the Medlin model, right, this is basically the G1 parameter. But if you're not familiar with that, it's just a sense of water use efficiency. And again, much like before, we sort of get these the scatter, but also patterns like highlighted on the screen here for grasses and for boreal regions that are consistent with our prior expectations. So we have these pretty pictures. Right now, what we want to do is actually improve land surface models, and that's basically exactly what we're working on next. All right, so that's one application. Another quite relevant application is what we might be able to do with microwave remote sensing to estimate patterns of drought-driven tree mortality. And that's really become an increasingly significant concern as you know, droughts have become more frequent and hotter due to global environmental change, right, in this AGU section we're in here. So I just put a little news release up here at the top of the screen, right? The most recent California drought, not the current one, was particularly sort of exemplifying this problem. More than 100 million dead trees in the Sierras, and some years, you know, 6%, 1 in 15 trees dying due to the drought. And there's some laboratory evidence from saplings that the probability of mortality really increases significantly as the water content in those saplings drops below a threshold. And so that relative water content is exactly what we're measuring in microwave remote sensing. So we wanted to see if that concept actually translates to ecosystem scales and can be useful there. And to do that, what we did is we said, okay, well, we want to test this, but you know, drought-driven tree mortality is sort of an infamously difficult thing to estimate, and there's a ton of different conceptual models out there. And you know, we want to be able to answer this question without having to kind of pick a conceptual model or process model of tree mortality, because there's so much uncertainty about those. So instead, we just used a machine learning approach. We used a random forest specifically, and I really like that pun, but it wasn't because of the foot pun. The random forests are useful here. And so what we did is we just trained that random forest model with relative water content data and a ton of other vegetation, climate, topography data to just have the machine learning tell us, you know, how useful these different data sets are. Now, the first step for doing that is you have to make sure you can train a model that's actually any good. And so, you know, you can see here in the bottom of this slide that the sort of patterns of mortality rates, the fractional area of mortality, were able to capture pretty well across California in this particular study. And when we then go look at that variable importance from the machine learning, we see that the relative water content, right, is very useful. It's more than twice as useful as the next variable as any other variable. So that suggests that microwave remote sensing can be useful for drought-driven tree mortality studies. And then the last example I'll sort of give here on the utility of microwave remote sensing is about wildfires and fuel flammability. And fuel flammability is a known factor in wildfire risk. I think hopefully it's somewhat intuitive, right? That if you have something that's dry, that's going to burn more easily than an equivalent wetter piece of fuel. And in the wildfire community, this is generally expressed in terms of this fuel moisture content, or if you're talking about live vegetation, the live fuel moisture content, the LFMC. And that's just defined according to this equation on the slide here. It's the weight of water in the live vegetation fuel divided by its dry weight. And so you can see again here that weight of water is coming in, that's tied to that vegetation water content that we can measure with microwave remote sensing. And so in fact, we took advantage of that to do just that, and we built high resolution, right, 250-meter maps of live fuel moisture content for the entire Western United States. This was sort of the first time this was driven by microwave remote sensing data and their sensitivity to water content. And, you know, I like to think that this is potentially useful for wildfire studies because really outside of remote sensing, you know, our knowledge of LFMC and how it varies was measured, you know, based on these in situ measurements that are super laborious, that require drying and all this complicated stuff. So we only had very sparse measurements. And so to illustrate that these data are potentially useful, we wanted to answer a question related to the plant traits that I was mentioning earlier, right? And we sort of said, okay, well, we have these stomata, xylem, rooting traits that we know influence water content and therefore LFMC. Is that effect actually large enough to significantly affect the spatiotemporal patterns of fire vulnerability? Now, I've shown you some maps of those traits before, but those are pretty coarse resolution. So in order to take advantage of our 250-meter resolution on the LFMC data, we kind of mapped an integrated plant water sensitivity effect, and that's shown in this map, right? And once again, you see sort of some patterns that you would expect, but also a lot of scatter because of all the factors I mentioned before. But now that we have this map, we can basically just go look at how wildfire risk changes in different pixels with different plant water sensitivity, even if those different pixels aren't next to each other. So when we sort of do that and aggregate this effect, and we look at burned area and its sensitivity to an increasingly dry climate, we see that there's a really significant effect here on the plant water sensitivity, right? So the difference in the y-axis here between the places with the highest sensitivity is they're going to be more than twice as vulnerable as the places with the lowest sensitivity. And that's significant because this is really not something that is accounted for in any wildfire models. I think arguably perhaps because we haven't really had the data. But you know, you saw the scatter in that plot. This is dependent on a ton of different vegetation properties, and just none of that is accounted for in LFMC evolution in wildfire models. So once again, I think this just illustrates another area where microwave remote sensing can be useful in the study of plant water stress response. And I'm not the only person who thinks that. So if you're interested in this beyond the couple applications that I just wanted to go through to illustrate here, I really encourage you to check out this paper that's now in press at Global Change Biology. This is really a perspective piece. It's not just my super biased opinion, but that's the result of a nice workshop that I organized with several other people at the Caltech Keck Institute for Space Studies shortly before the start of the pandemic. Yeah, so check that out if you're interested. And then I'll just briefly put up some conclusions here, right? I hope I've convinced you a little bit that observations of vegetation water content from microwave remote sensing are sensitive to and indicative of changes in relative water content and water potential, that we can use those to map ecosystem scale hydraulic traits, but that there's also a ton of other applications, such as in drought-driven tree mortality and wildfire risk. And I think I'll leave it at that. Thank you.
Okay, thanks very much, Alex, for that. I have a lot of questions, and like everyone else, we'll wait until after the second talk, and then we'll dive into questions. And I just want to remind everyone to please put their questions in the chat as we segue now on to celebrate one of our other early career award winners. That's Kim Novak, who's an associate professor in the O'Neill School of Public and Environmental Affairs at Indiana University. Her research focuses on understanding how climate variability affects ecosystems and the complementary processes by which ecosystems alter climate at local and global scales. Much of her work relies on the synthesis of data aggregated in environmental observation networks, and she serves in a leadership capacity in multiple networks, Ammerflux, FluxNet, NSFs, EON, and so on. So we'll let her tell us more about what she's thinking about today. Go ahead, Kim.
Okay, thank you, Julie. Can you all see my slides?
Yes, we're seeing them.
Terrific. Okay, let me make sure I can see them. Well, thanks to Julie and the GEC section for the opportunity to participate in this webinar and also for the award, which I'm just thrilled to be able to share with Alex, who I've had the pleasure of knowing for most of our quote unquote early careers. So the topic of my talk is natural climate solutions, and I'm going to caution that this is going to be kind of a forward-looking talk, presenting a lot of work that's sort of on review or even in prep. But before I get there, I do want to start with a bit of a retrospective, just showing two figures that tell some similar refrains in terms of rationale, not only for the work that my lab does, but that for the work that a large portion of my field has been doing now for decades. Right, so on the left, we see a figure that illustrates the fact that the terrestrial biosphere is an important but variable sink for anthropogenic emissions of CO2, giving us roughly a 25 or 30% discount on anthropogenic greenhouse gas emissions. On the right is a figure that shows different Earth system model projections for the global land carbon sink moving from 1850 to 2100. And the story here is that while most models agree that right now, indeed, the terrestrial biosphere is an important carbon sink, as we look toward the future, the models begin to disagree on the magnitude and even the direction of land carbon uptake. Right? And this uncertainty propagates through into uncertainty in our ability to predict future climate conditions and thus prepare for and adapt to them. Okay, so this is a big problem. And it's not particularly surprising that the models have such a hard time with this challenge because the terrestrial carbon cycle is a very complex system. It integrates processes occurring over scales as small as cellular in the case of photosynthesis, up to entire plants and then entire ecosystems and entire landscapes with a lot of interactions between the different components, many of which are themselves sensitive to ongoing climate feedbacks. Right, so kind of a wicked problem and very complex. But undaunted by the complexity of the problem, we have invested globally and nationally huge amounts of time and energy and resources into tackling this research challenge. One of the most useful tools has proven to be flux tower networks like Ameriflux and FluxNet. Flux towers are the only measurement tool we have that allows for direct observation of the movement of carbon dioxide between ecosystems in the atmosphere. They also measure related energy fluxes and water cycle fluxes. We've also confronted the problem with big, grand experiments with a growing set of remote sensing platforms that can detect not only ecosystem structure, but also function. with VOD being an excellent example. Thank you, Alex. Models that are ever growing in terms of their process richness, and then even new strategies for training the next generation of scientists to work with these disparate tool sets and across disciplines. But we, despite all this investment of resources, we haven't solved the problem. Here it is in 2006, and here it is in 2014 in different colors. Progress can even be hard to measure at times. And we should keep trying, right? Because there's always the hope, maybe, that we sort it out. From my perspective, even more importantly, is that along the way, we have learned a lot about the individual pieces of the puzzle. And it turns out that understanding controls on ecosystem carbon, water, and energy cycling is knowledge that is highly relevant to a number of other pressing research needs that are becoming even more important as the impacts of climate change are becoming more sensible. Right, so some examples of areas where my lab is beginning to focus our attention include drought monitoring, agroecosystem sustainability, and then the topic of this talk, natural climate solutions, which I'll introduce in the next slide. But just again, to summarize here, yes, we should continue to work on the very hard problem that we've been working on for a really long time, but let us not forget to pause and maybe appreciate the ways that our knowledge and data can be useful for other really important applications. All right, so what are natural climate solutions? Well, the idea is that we know that ecosystems are an important carbon sink, so can we manage them so that they take even more CO2 out of the atmosphere? Or alternatively, reduce emissions of other greenhouse gases like methane and nitrous oxide. This is an incomplete laundry list of some viable natural climate solution strategies for the United States. You can see that reforestation comes out on top as having the overall highest carbon mitigation potential. We have to recognize that these are not a panacea for climate change, right? The way to stop climate change is rapid and economy-wide decarbonization, full stop. Okay? Natural climate solutions, nonetheless, are part of most pathways to net zero. And they have some attractive co-benefits. A lot of them look a lot like restoration, right? And so thus they have benefits for air and water quality, for biodiversity, for soil health, and offer some potential for local climate adaptation in some cases. There is, however, an awful lot of uncertainty about their mitigation potential. More on that in a couple slides, but one illustration of that is right here in the size of these error bars. There are a number of policy mechanisms that could be used to implement natural climate solutions, including practice and performance-based subsidies, as well as public and private carbon market systems. Right now in the United States, this is the primary tool in place to upscale natural climate solutions as a mitigation strategy, and most of these tend to be voluntary. It's tempting to think that there's some sort of orderly system connecting landowners in a position to implement a management shift with corporations or other entities interested in offsetting their emissions, involving project developers, brokers, accreditors, and some third-party verifiers. In reality, the words that are often used to describe the private market system include jungle or Wild West. The truth is that there are an awful lot of actors and an awful lot of entities, and there's more coming online every day, and the relationships between these different entities are not always clear. It's very hard to see the landowners in this picture, which is a problem because in fact this system is really inaccessible, at least to owners of land that is small in size, okay, which is a problem. Despite the complexity of the market system, natural climate solutions have a lot of support from a really unusual coalition of actors, including both conservative and liberal lawmakers, including Indiana conservative Senator Mike Braun, who is the leading sponsor of a bill that passed the Senate in July called the Growing Climate Solutions Act. There's tremendous enthusiasm in the private sector, as we saw on the last slide. Conservation groups like the Nature Conservancy are really excited about these ideas, not only for their potential climate benefits, but especially those co-benefits. And there's even at least lukewarm support from places like the Farm Bureau and the timber industry. Okay. Despite this enthusiasm, there remains substantial uncertainty surrounding the realizable benefits of natural climate solutions, not only about their global climate mitigation potential, for example, with respect to CO2, but also a lot of uncertainty about the extent to which these strategies might impact water and energy cycling locally in ways that may or may not be climatically beneficial. Given the groundswell of support from so many quarters, right, it's reasonable to expect that these are strategies that we're going to be having to contend with moving forward, and thus there is a lot of need for new approaches for natural climate solution assessments at policy relevant scales, so that state and federal lawmakers can know when and where a particular strategy will be effective. There's a need for new approaches for quantifying the realized benefits of specific carbon mitigation projects. And there also is a need for new approaches for systematic quantification of these biophysical co-benefits or sometimes unintended consequences. And that motivates the rest of the talk. I'm going to discuss, in broad terms, some of the difficulties in assessing natural climate solution benefits, propose some path forward, and then end with a case study looking specifically at biophysical impacts of one natural climate solution strategy, Eastern US reforestation. Right, so why is this so hard? Why are we so unsure, right, about the realizable potential of these strategies? A lot of it has to do with the fact that in both the existing regional scale assessments and project level verification, the primary data sources and variables of interest tend to be point or tree scale. So in agricultural systems, the variable that tends to be monitored most closely is soil organic carbon change, which can be measured through physical sampling of the soil and also modeled using generally fairly empirical approaches. In forested ecosystems, we're looking primarily at above ground tree biomass and carbon content thereof, which is estimated by measuring tree diameter and tree height, and then forcing those data through allometric equations, which are again quite empirical. These measurements are easy and cheap to make, which is not a bad thing. However, this approach has a lot of downsides. We're really measuring only one pool of carbon in these ecosystems, and so there's the potential to be missing important sources and sinks, for example, loss of carbon through runoff and outflow, changes in soil organic carbon in forested ecosystems, and on all places, changes in carbon in deeper soil layers. The approach usually isn't able to fully capture gradients in soil organic carbon or tree biomass within an ecosystem, which can lead to bias. And really importantly, it takes a long time for these pools to respond to a management shift, right? You might have to wait 3, 4, or 5 years before you find out if a carbon mitigation project is having the intended effect, which is a problem generally and especially for the market systems. So consequently, we have big mismatches in scale between the plot level where these data are collected, the ecosystem scales where project benefits are calculated, and then regional scales where policy decisions are made. And to an extent, satellite data can help us with interpolation and extrapolation, but the output will only be as good as the underlying data, which for many NCS strategies is quite sparse. Okay, we don't have a lot of data, for example, on the effects of biochar on soil organic carbon content, or even cover crops for that matter. Consequently, spatially explicit maps of the potential of many NCS strategies do not yet exist, and those that do tend to be limited to forest, where they are often focused only on a single carbon pool, which is above ground biomass. Getting back to this notion of biophysical impacts, this is a paper that came out about the time I was starting graduate school and made a big impression on me. The authors of this study showed that especially in semi-arid locations, tree plantations, right, designed to enhance carbon uptake had a really deleterious effect on local stream flow, which is definitely undesirable biophysical impact. When I get to the case study, I'll show that sometimes these biophysical impacts can also be beneficial, but we really don't have systematic assessments for the full suite of proposed NCS strategies. And then there's also finally the huge problem of permanence, which is linked to the fact that future climate feedbacks like increased droughts, increased wildfire risk, increased risk of insect outbreak have the potential to wipe out decades worth of accumulated carbon in ecosystems in an instant, especially in forest projects. And it is critical to know that the accounting and verification protocols used by the carbon markets really don't consider the potential for these feedbacks and their threats to the permanence of stored carbon at all. All right, so that's enough problems. let's discuss some potential paths forward. All right, so what can we do to confront this uncertainty surrounding natural climate solutions? And the material I'm going to present here in this section really comes from two sources. The first is a paper published earlier this year by the talented Kyle Hemmes, and the other is a paper in prep emerging from a new Ameriflux Network Natural Climate Solutions Working Group. And our contention, particularly in this paper, is that we don't need radical shifts in research infrastructure to be able to address these knowledge gaps. And in fact, we have the tools at our disposal because, again, we have been studying terrestrial carbon cycling for decades. The challenge is that with the exception of those shown here in the lower left corner of this figure, and to an extent some remote sensing data, most of these tools have not been systematically assessed to understand the potential of natural climate solutions. Excuse me. Because this paper is emerging from the Ameriflux working group, I'm going to focus now specifically on some strategies to better harness the information provided by flux towers and flux tower networks. So there's, in fact, huge opportunity to leverage data that are already existing and, in fact, already shared and publicly available. So right now, the Ameriflux network has data from more than 405 towers shared to the network, with another 150 towers registered but not yet sharing data. Of these 405, 150 are forest ecosystems, and we have dozens of croplands and grasslands in the network too, right? So we are very data rich. And there's a particular opportunity in leveraging what I'll call paired sites, which are ecosystems that have flux towers that are located close together, so they experience the same climate but differ in land management. So a really good example is a set of 3 towers from the Duke Forest. I spent a lot of time hoofing around here as a graduate student, but we ran towers in an old grass field, a pine forest, and a hardwood forest for 8 years. And we really hammered those data and looked at them a lot of different ways, but we're able to show, for example, that the pine forest and the hardwood forest are strong and persistent carbon sinks, which is a particularly important finding in the case of the hardwood forest because ecological theory, existing ecological theory tended to predict that by the time forests reach maturity, they'd be returning to carbon neutrality, and that's not what we observed. We showed that these forests use more water, and we also showed that the surface of these forests is relatively cool when compared to the surface of the grassland. More on that in a minute, right? But these towers really allow us a holistic perspective, not only on the mitigation potential of land cover changes, but also these biophysical impacts. We can also consider using these flux towers as anchors for upscaled flux products where machine learning has a lot of potential here. The procedure is conceptually fairly simple. You gather flux tower data together with gridded inputs from these so-called flux towers in the sky, our remote sensing products, and develop a predictive model that can allow us to create wall-to-wall flux maps. So there are some machine learning flux upscaling products that already exist. A very popular one is called FluxCom, but most of these tend to be global products informed by a subset of flux towers from all over the globe. So we contend that particularly for addressing uncertainty related to natural climate solutions, there's a lot of opportunity around creating more regionally constrained flux upscaling projects, for example, maybe just for the Corn Belt, or maybe just a particular biome, for example, eastern US forests. And another thing that's fun to think about is the potential of what I'll call gold standard data sets, where we can imagine that we have not only long-running flux towers, but also sort of a full suite of biometric on-the-ground measurements together with near surface remote sensing data from a representative set of ecosystem types. And then we can make these data, of course, free and open and easily accessible, where they might serve as a foundation, for example, for transparent intercomparison of market protocols, right? Because there's a lot of variability within the carbon markets in terms of the verification standards and approaches, and we could use these data as a way to get a handle on that. Imagine a carbon market model intercomparison project. We could use these data to understand biases among different data sources, for example, comparing what we think we know from tree inventory data to what we think we know from flux tower data. And they can also serve as a functional test bed for new verification or upscaling schemes. And then finally, when it comes to specific projects, right, credits sold on the carbon markets, the benefit cost ratio for using flux towers as a monitoring tool honestly isn't that great because they're expensive and difficult to operate. But somewhat paradoxically, it actually improves for taller towers, which could be used to monitor larger projects. And the reason for this is that each half-hourly carbon flux measurement is associated with a unique footprint of the land surface. So over time, for a very tall tower, you're actually sampling a fairly representative set, or representative, let's say, subset of the surrounding landscape. So again, using machine learning approaches, for example, you can sort of virtually extend the tower footprint so that's 10 to 100 times greater than an individual tower footprint. Okay. And so finally, I just want to spend the time that I have left digging a little bit more deeply into this topic of biophysical impacts, also cognizant of the fact that I've shown very few results in this talk, so this will give us a chance for me to talk about some of the work that my lab members have done. But I want to talk specifically about biophysical impacts of eastern US reforestation, which is an interesting case study. We know that eastern US forests are relatively strong carbon sinks, right? So their carbon mitigation potential is relatively high. These forests are very biodiverse. They have dozens of tree species, which makes them relatively resilient to drought and insect damage. It's a wet part of the world and getting wetter, so wildfires are relatively rare. In the eastern United States, forests regenerate on their own. Stop mowing a grass field and a forest will come back, right? No tree planting necessary. And there's also been, interestingly, a general trend of reforestation in the eastern United States over the past century. Very brief history, prior to European settlement, forests dominated the region across the eastern United States. As colonizers moved west, they cut down nearly all of them. At some point, the extent of deforestation was greater than 90%. But by the time we got to the 1920s and 1930s, many of these croplands had fallen out of productivity. And then as we got hit with the Depression and the Dust Bowl, a lot of those farmlands were abandoned and have slowly been regenerating over the past century. Certainly not all of the forests that were originally present on the landscape have regrown, but a substantial fraction has. And an interesting question, or another interesting thing I should say about the region is that it's a part of the world that hasn't warmed as much as most of the rest of the land surface. So this is a change surface temperature trend for the past century or so. And what we see is a so-called warming hole over the southeastern and south central United States. And there's been a variety of proposed mechanisms for this warming hole, including ocean oscillations and irrigation and a few other things, but it's not quite settled what's really behind it. So a hypothesis we're testing is that this long-term trend in reforestation may be playing a role. And why might we imagine that it could be? Well, there's a few mechanisms by which a land cover shift can induce a change in temperature. As we move from, let's say, a grassland to a forest. On the one hand, the forest will be darker. They'll have lower albedo, which would tend to warm the surface. But on the other hand, forests use more water. They have higher latent heat flux or evapotranspiration, which is a cooling process. Forests also have higher sensibly heat flux, which at least moves heat energy away from the surface into the atmosphere. Okay? So whether or not the surface of forests are cooler than grasslands really depends on the interplay between these three factors. And then whether or not a surface cooling extends to the near surface air temperature, which is arguably the more relevant variable for our purposes, is going to depend on some complex feedbacks occurring in the boundary layer. Okay. To address the question, we first used this sort of gold standard paired flux tower approach, where we found 6 co-located grassland and forest flux towers across 5 different parts of the eastern United States. And using some data published by my former postdoc Quan Zhang in a paper that came out last year, we were able to show that the land surface temperature of forests is substantially cooler than nearby grasslands during midday periods of both the growing and dormant season, where during the summer it was evaporative effects primarily responsible for the cooling, and in the winter it was aerodynamic effects. We can also address the question using remote sensing land surface temperature data, and this is work being done by my former postdoc Mallory Barnes, who looked at the difference between land surface temperature data measured by MODIS and day met air temperature, where we can treat day met as sort of it's kind of like a reanalysis product, which we think should be relatively insensitive to local land cover. So it's sort of like a normalizing variable. And what we find is that indeed, again, the forests tend to be cooler at the surface than the grasslands and the croplands most of the year. Whether or not this surface cooling extends to the near surface air temperature is a much harder question. We can't measure near surface air temperature directly from space, and it's actually hard to get a handle on it even from our flux towers, because the canopy elements can really dramatically alter the shape of near surface scalar profiles, especially above forests where the roughness sublayer can often extend above the flux tower itself. So in a paper that came out last year, we explored some strategies for looking at air temperature metrics like the aerodynamic temperature and air temperature extrapolated into the surface layer that should be less sensitive to canopy effects on the local temperature profile. And when we do that, we find that whether the metric is surface temperature, aerodynamic temperature, or extrapolated air temperature, that forests tend to be cooler than croplands or grasslands. Here, these data are coming from a synthesis of more than 50 flux towers across the eastern United States. We can even see a pattern, though these results are probably not significant, in the tower-derived air temperature, but keep in mind again that those data are very sensitive to canopy effects on the local temperature profile. Okay. I'm going to skip this slide because I'm running out of time, but we also took a number of different approaches to try to fingerprint the effect of reforestation and land cover on air temperature changes. And overall, this is work that we hope to submit soon. We conclude that in the eastern United States, reforestation cools the land surface by quite a bit, especially during midday summer periods when arguably we need the cooling most. That the cooling extends to the near surface air temperature, which is important if we want to fingerprint reforestation as a contributor to the southeastern warming hole. But the magnitude for air temperature effects is a bit reduced. Nonetheless, it appears that reforestation could explain some, but not quite all of the eastern US warming hole. But what this means generally is that for an NCS strategy like reforestation, where we know that there is a substantial carbon mitigation benefit, there appears to be also a climate adaptation benefit. Okay, how we include that benefit in policy setting or in market valuation is definitely an open question, and a lot of work needs to be done in that vein. So last slide, just to summarize. Generally speaking, the actual benefits of natural climate solutions are uncertain and difficult to quantify for a number of reasons, but many of them are linked to these scale mismatches between the data that we have, right, and the variables that we want to understand. Substantial opportunity exists to confront these knowledge gaps using tools like flux towers and flux tower networks and next generation remote sensing products that we already have at our fingertips. And as we engage with this work, let's not forget the importance of considering biophysical impacts along with carbon mitigation benefits. So thanks to the GEC section, to collaborators and to funders. And if you want to join the AmeriFlux Natural Climate Solutions Working Group, send me an email. Likewise, if you're interested in the next offering of Flux course, which will take place in Colorado next summer, keep your eye out for details or send me an email. Thank you.
All right. Thank you very much for your presentation, Kim, and thanks to both of you for really stimulating talks. And I just want to ask if people would put their questions in the chat. A couple of us will try to monitor that. And one question I have, maybe to both of you, I'll just start out while people are thinking about questions. So I'm not so smart as a geologist about stomata hydrology and how that all works. And as we, what I can remember learning at some point was that as CO2 goes up, the number of stomata goes down. And so I was just wondering, as we go into, now that we're at 420 parts per mil CO2 and going higher, how does that CO2 versus the evapotranspiration, how does that work, and what does that mean about drought, stress, and increasing CO2 at the same time? And I'm sorry if that's an elementary question, but who would like to answer that?
I'll take a stab at it and then Alex correct me. Anyways, You know, it is a really important question, and it's interesting because the data we have to confront that question, right? How does rising CO2 affect stomatal conductance tends to be limited to experimental data, for example, from the face sites, or more like plant scale data, right, or data from growth chambers, right? So we don't have, you know, historically, we have not yet had long-term observations that could allow us to get at that question quite as easily as we can get at some of the other questions, for example, about soil moisture, VPD constraints on stomata. But I think that our flux tower records are now getting long enough that we might be able to make some progress on that question in the future. But I mean, we know that you're absolutely right that rising CO2 should be expected to reduce stomatal conductance, and we can play games, you know, by adjusting the stomatal conductance parameters, at least in models. It's likely to, I would say, mediate, right, drought impacts in the absence of that particular adaptation mechanism.
So, Alex, do you
I
have
think
anything?
Alex was trying to say something, but I think her unmute has some issue.
Okay, go ahead, Alex.
Alex, we're still not hearing you. I'm not
Okay,
sure.
but now.
Yep.
Great. Okay, I was getting a lot of messages about permissions I couldn't quite understand. But yeah, I mean, I think Kim gave a great answer. Maybe what I'll just briefly add is that you know, we can understand this so far, but going forward, you know, the existing record will only tell us about existing CO2 conditions, past CO2 conditions. So going forward, you know, there's still a lot of uncertainty about how that response to CO2 and drought will continue to evolve, that we can partially address with the existing data, but not fully. And I think maybe the other thing I'll just throw in the mix here, just because I know it's a topic that is dear to both Kim and I's hearts, and neither of us really had time to get into it, is that drought stress in and of itself is kind of an intriguing concept that I at least in my talk, played super fast and loose with, because there's sort of multiple components in that. On the one hand, there's an absence of precipitation that might induce drought stress. On the other hand, as temperatures are getting hotter, the atmosphere essentially is getting drier, just because how much moisture you can hold in the atmosphere is something that changes really dramatically with temperature. And so that ends up basically like sucking more of the water, or putting more pressure to suck water out of the land surface. So there's also a sort of, as part of, I think, a challenge in this field is to understand how CO2 changes and drought stress changes and other global changes all interact in this wicked problem that Kim mentioned. You know, there's also an aspect of understanding precipitation versus evaporative demand as different components of water stress. Just to make it more fun.
Yeah, thank you. Yuhan, do we have more questions?
I do have a question for both Kim and Alex, which both of you have mentioned a lot about data in your talk. So the question I had is, when you have unlimited investment that you can invest in, what you will be investing in making sure that you get enough data or the appropriate data to improve our understanding. So both of you can answer that. It's a wide question.
What's it?
You say we might have different answers. I'll go first. So I you know, I'm traditionally, I guess the word is observationist. We do a lot of field work. My lab does a lot of field work. So my mind, when you pose a question like that, tends to think about field observations. And truth is, we have so much data out there already that I think, you know, the first thing is to take stock of what is available and do the work that is necessary to make sure that what is available is accessible and open to a wide variety of audiences. You know, sometimes the data may be quote unquote accessible to the experts in the field that know how to understand it, that can be actually quite inaccessible to somebody that understands it in theory, but just isn't used to the particular data formats. From there, you know, I think that it's important to look for opportunities to fill gaps. So one that comes to mind for me is observations of water potential, both in the soil and in the plants. You know, we now have these really great ways to get at it using remote sensing data, but our ground observations of water potential tend to be rather sparse, particularly in places where we're also measuring things like eddy covariance fluxes. So thinking about, targeted networks to fill the gaps that we really need to give us this holistic picture on carbon, water, and energy cycling is where my mind would go.
Yeah, I mean, we do not have different answers. I 100% agree. I think, from my point of view, as someone who works a lot with remote sensing data is only as good as our ability to really test it and validate it on the ground. And water potential, and particularly something where we just don't have as many data sets on the ground as we have for many other related variables, despite sort of its importance. So I think that could help dramatically. The other thing I'll mention, just to kind of harken back maybe to Kim's point in her talk about most of the work on natural climate solutions being focused on understanding how much carbon is stored in biomass. One area where remote sensing really has a lot more limited capacity is in looking deeper into the ground and at soils. And so more sort of deeper soil carbon measurements, even though this is not an area I work on at all, but it's just a personal side interest of mine, I think would be quite useful.
And there's always the potential that the things that we can see, the vegetation, can provide us some clues about what's going on below ground if we have the right ground truthing data sets. So with water potential, the answer is it's kind of clearer because at night there's a general assumption that at least sometimes the plants and the soils will equilibrate. So if you can see what's happening with the plants, then it's a window into what's happening in the soils. In the case of carbon, it's maybe a little bit more complicated, but we have certainly plenty of informatics tools at our disposal to detect a signal if one exists.
Great, and we do have a question for Kim. Julie, do you want to ask that question? Oh, I can go ahead. Yeah.
Go ahead because I don't, for some reason, I'm not seeing it.
Okay, cool. The question for Kim is, how do you think the climate impact of Eastern United States forests will change as this forest undergo transition from earlier to later succession of species? And the people who are asking these questions' impression is that carbon sequestration slows down later into succession, but I have no idea about some of the other climate impacts you mentioned, such as energy balance, plant-water relations. So do you have any thoughts on that?
Yep, I do. I sort of blew past that in the talk. There's a famous ecologist, Eugene Odom, who worked in the Southeast United States, who published a very highly cited paper, still cited all the time to this day, suggesting that once forests in the Eastern United States reach maturity, about 100 years old, that they become more carbon neutral, right? The data from our study sites in the Duke Forest and also all the other data in the AmeriFlex network suggest, we cannot conclude that Odom is wrong, but merely that his timeline is off, because we see that, forests that are a century old are still fairly strong and persistent carbon sinks. Now, certainly it's possible as they continue to mature in age that we'll see their uptake potential decline. The problem is there's hardly any old growth forests in the Eastern United States, because remember, we cut down all the forests in the 19th century. So we're just going to have to wait and see. But the good news is that the forests that started regenerating in the 1930s are still strong carbon sinks and should be for some time. As for water and energy cycling, there's reason to believe that these two, that those two, evapotranspiration and land surface temperature, might be closely coupled to carbon uptake, especially for the case of evapotranspiration. But there's also a lot of interplay between transpiration from plants and evaporation from bare soil that might mute some, or might decouple those variables a little bit. In case of land surface temperature, because a fair amount of it is driven by these aerodynamic effects linked to canopy height, I wouldn't necessarily expect that the, let's say, cooling benefit would follow the same trajectory as carbon benefit over long time scales.
I think I'm muted.
Yep.
Thank you. And I do have follow-up question for both Kim and Alex, which in both of your talk, you mentioned about machine learning, and what do you see? You show the potential, and what do you see the limitation that we're currently dealing with machine learning, and how that can be improved when we are addressing the issues that you're talking about?
Yeah, I mean, I think maybe I'll go first on that one. Certainly, there's great potential to machine learning. I think there's that's shown actually in both Kim and I mentioning that. There's a couple different downsides. One is that if you're trying to make future predictions, the data is only again as good as what you have been able to observe in the past. So there's sort of a stationarity problem, right? You can't go outside the domain over which you observe. I think a sort of second question about machine learning that personally interests me a lot is that generally, I think once you try to use machine learning in sort of a global environmental change setting, the instinct is often to think about how you're limited by data and to try and find better training data, better input features into your machine learning. Those issues are certainly really relevant, and I think often extremely limiting, right? We used about 120 training sites over the entire Western US in our live fuel moisture content data set, for example. But honestly, I think there's also just a little bit of a skills gap in the sense that if you actually talk to computer scientists working on machine learning and you explain some of these sort of problems that we're working on, they seem a lot less convinced than people in our field that the only limitation is training data. And I think fundamentally we don't really know, and so there's also just a communication gap in making sure that we're not just using the most basic machine learning techniques as well. Now, I think that's an issue that is a little bit farther out. Like there's a lot of things that we can still solve even with very basic machine learning and improvements to be made. But it's an interesting one, on the horizon as well.
Kim, do you have anything you want to add?
I think Alex gave a great answer. I should clarify, I don't know how to do machine learning. I'm just lucky to work with people that do. So I'm probably not qualified to say anything beyond what Alex said.
I think there's like two relevant events going on this week, actually. One is the Department of Energy. They have an AI for Earth system predictability workshop that's going through for like 5 or 6 weeks. And the other is the analysis ready data for Earth observation workshop that's linked really closely with what Kim and Alex just discussed here. So I'd recommend everyone who can go to find those events ongoing. Julie, do you have anything you want to add?
No, if there aren't any other questions, why we can wrap up. Is that okay? Yeah. Okay. Well, I just want to take this opportunity to thank both Alex Cunning and Kim Novak for wonderful presentations, and we really congratulate you on your work and look forward to possibly seeing you at AGU in New Orleans. If not, we'll see you virtually. And I want to thank all of the participants, and I particularly want to thank Yuan Rao for organizing and keeping these things going, and also to Hannah Hoffman, who is from AGU, who's running the show. Thanks to all of you. And we will celebrate 2 more people next month. We'll be announcing that on the AGU Connects, and invite everyone to look forward to that. So with that, I hope that everyone will give a virtual clap to our speakers, and thank you very much.
Thank you so much for the opportunity.
Yeah, great. Thanks to you all. This was fun.
All right, thank you.
Thank you.